All right, so today we are talking about regularization. So as far as business, project 4 is due this Saturday. So last time we talked about algorithms for style transfer, a base algorithm and a couple of variations, some that included real-time style transfer, others that allowed us to control where in the image different styles were applied. We talked about how, like, while that's kind of a niche use case, it helped us understand a lot more about how to design a loss function and the different ways we can think about optimization, not just optimizing the weights of the neural network, but optimizing over perhaps the inputs to our neural network. So I want you to just take a couple of minutes, turn to the person next to you, and try to explain how style transfer works.
A couple of minutes. You've already trained to do this. One of them is trained to given an image, given the style of the axis.
What is the concept you use? I think there's one single network that you have like a backstop. Banking up the idea really I'm describing it kind of cool.
All right, can I get a volunteer to explain either intuitively how style transfer works or mathematically what's happening? Yeah. Yeah, there were some good elements in there. So we're using a trained neural network to extract features from both a style and a content image. You mentioned erasing locality, and I'm going to make a slight correction there. So you talked about you erase locality by stretching out the height and width. That doesn't erase locality necessarily because the height and width information is still there, even if we're just changing the arrangement of it. What erases locality is when we take the dot product across height and width, collapsing that height and width dimension into a single number. And so, and that applies only to the style network. So remember, for the content, we're taking all of those features, stretching them out, and then just trying to match those features, including matching them spatially. And that's what allows us to preserve the spatial arrangement of objects in the image. Whereas for the style network, we're taking that dot product, creating the gram matrix so that we only have the correlation of certain features with each other. And then we match those feature correlations on the style set. Great. Any questions on style transfer? Yeah, Brendan.
The combination.
So the combination. Yeah, so our loss, if you remember, is a weighted sum of a style loss and a content loss. And the trade-off between those is controlled by a single hyperparameter, which we call alpha. And I think normally we set alpha to about 0.001 or something like that. Okay. So today we are talking about batch normalization as well as regularization. And then if we have time, we'll talk a little bit about our final project. So if you remember from our lecture on initialization, we saw that sometimes you had to change your initialization strategy based on which activation function you were using. We saw that when we used Xavier initialization for ReLU activation functions, our gradients ended up disappearing. And so P initialization divided that initialization by the variance of that initialization by 2 and allowed us to have our gradients travel once more with the ReLU activation function. But you can imagine that this could lead to failure cases if you don't know exactly what you're doing with your initialization and how each of those works with activation functions. And so there's this idea of batch normalization, which basically says we don't want our network to be thrown off by not being able to predict the by having inputs that fall in unpredictable ranges. And so what we're going to do is we're going to normalize our inputs every layer by making the inputs every layer have mean 0 and variance 0. Or not variance 0, mean 0 and unit variance, so variance of 1. And so to do that, we take our inputs to a layer, we subtract the mean of those inputs, which will make them centered at 0, and then we divide by the standard deviation or the square root of those inputs, and that will make them have a standard deviation of 1, which is the same as having a variance of 1. So that is just a diagram of what I just said. Okay, as far as where we apply it, we usually put it between the output of a layer and before an activation function. But this kind of gives rise to another problem where, again, the behavior of different activation functions differs depending on, basically different activation functions want their inputs to have different mean or standard deviation. And so to account for that, we are going to normalize and then allow our network to choose the mean and variance of the inputs to each layer. So this is how it works. So we first take our unnormalized inputs, x, and normalize them to get x hat. And what is the mean and variance of x hat? 0 and 1. Yep. And then we're going to transform x hat and basically re-stretch it and reshift it. And that's what's happening here. We're going to stretch it by a parameter gamma and shift it by a parameter beta to have a new variance and a new or a standard deviation and a new mean. And so this allows our network, and then both gamma and beta will be learnable parameters for our neural network. So just like our network learns the weights, we will allow the network to tweak gamma and beta to provide inputs in the correct range for whatever activation we are using. So basically, just like we like to do in lots of other things in deep learning, why not just let the network learn it? Let the network learn what mean and variance it wants for the input each layer. Yeah, question. Yeah, so this goes back to the lecture on initialization, where we saw, and on activation functions, where we saw that if we recursively apply the same activation function to the outputs to unnormalized inputs, it ends up pushing the values in a certain range to a range where we no longer have any gradients, where our activation function saturates. And so because of that, we like to kind of recenter our inputs at each layer so that we're still getting meaningful information out of each activation function. Yeah.
In your experience with batch normalization, when do you want to apply this rigorously to your network, and when do you sort of leave it as a
Batch norm is usually a good idea to move batch. Okay, so yeah, this is the full algorithm. So we take a mini batch, we obtain the sample mean of that mini batch by taking the sum and dividing by the number of items. Then we will obtain the sample variance of that mini batch, and then subtract the mean from each item and divide by the variance. So a couple of benefits to this, like I mentioned, it improves gradient flow to the network. It allows us higher learning rates, and yeah, reduces our dependence on initialization strategy. And also can act as a form of regularization, which we will discuss later in this lecture. Yeah, so this is also something to keep in mind, and something to keep in mind in general as we learn about neural networks is that at training time and at test time, batch norm functions differently. So at training time, we're going to obtain our sample mean and variance from the mini batch, but at test time, we don't want to have any dependence on other data points. And so we will compute basically a whole data set mean and a whole data set variance during training time, and then store it, and then apply that whole data set mean and variance at test time, so that we can apply batch normalization to any unseen test data point without having a batch of items to normalize it. So this is how it looks in terms of, yeah, if we were to look at a tensor. So this is a three-dimensional tensor. Here we have stretched the spatial dimensions into a single vector, which we are calling H and W. We have channel dimension and then batch dimension, number of items per batch. And so we take the mean across the batch and divide we divide each element of that tensor by that mean. There are other variations of this where we can normalize across channels, or normalize across only height and width, or other segments of that tensor. Okay, so regularization. This is so in machine learning, we often have, well, we always have data, and we want to learn a function to fit that data. And so here's an example of some data that we might have, and we are trying to find a line. Our trained data is in blue, and then our test data is in white. And so we're trying to find a relationship between X and Y, and you can see that F2 is probably, if we were to look at both the train and the test data, this function is a pretty good fit to both the train and the test data. But if you look at F1 fits the train data even better than F2. But you can imagine that if you were to try to use F1 to predict the values of these test points, our error would be pretty significant if you look at the difference between the value of F1 and the value of each of those test data points. Yeah, question? We're normalizing between layers. So between the output of a weight layer and the activation. You do actually at train time, you normalize across the mini batch. So you take the average your features across the mini batch, and then you subtract the mean and divide by the variance across the mini batch. Yeah. Correct. And so if a data point ends up in mini batch one in one training epoch and ends up in a different mini batch in a different epoch, it's going to have a different scale, a different shift and shrink. It's going to have a different mean and variance that it's changed by. And you can think of that as kind of adding some more training noise to the training process, because you aren't shifting and scaling by the same amount every time. And that's why batch norm can be a form of regularization. Yeah, good question. So when we have a trained network and we want to use it, then we take the mean across the whole training data set and the variance across the whole training data set, and we use that as our mean and variance to shift and scale new unseen data. Each feature. The outputs of layers. Correct. Yeah. So we run our entire data set through the network, and we'll get, you can imagine it as one gigantic mini batch, and we'll get an activation map that is N by C by H and W, and then we'll take the average across N, and then the variance across N, and then we'll apply that data set mean and variance to all unseen data. Yeah, Jaden.
My debate, normalization that we're forcing all the activations of single layers to get a bell curve.
Yeah.
Points on a bell curve.
Yeah. Well, yeah, to follow the bell curve distribution with mean, zero, and variance. Yeah. Yeah, question. Good question. Yeah. So that's a good point to make. So for batch norm, we have two normal kind of normalizations that happen. One is when we adapt our data to be mean 0, variance 1, and then we have a learned part where we're learning that gamma and beta, where we learn a new variance and a new mean, and we shift the data to have mean and variance gamma or mean and variance beta and gamma. So the first step of batch norm is to make it mean 0, variance 1. The second step of batch norm is to make your data have mean beta and variance gamma. And gamma and beta. Okay. Dang.
Just 2 questions. Just to be clear, are we creating the bell curve fit at the granularity of each activation or the whole layer of activations?
Each activation will have its own gamma and beta.
Okay. And second question, when we're doing back propagation, because the activation values are relevant, do we use the normalized values or do we use the prior values for training?
No, you're using the normalized values. The batch norm is changing your data as it flows through the network. Yeah. All right. Yeah. Well. Right. Yeah, that's a great question. So I haven't ever seen a batch norm applied at the first layer of a network, like before everything else happens. And so you should probably still normalize the data before it goes into normal. And then batch norm will take care of making sure that the inputs to every activation subsequently are normalized. Yeah. Okay, so we were talking about how if you are overfitting to your training data, that can cause poor performance on your test data. And if you are familiar with machine learning, this should be a familiar problem to you. So regularization pushes against this effect where the blue curve fits our training data too well. That's just another example. Okay, so here's another example where we have our training data, and you can see several different possible curves that we could choose to fit this data. We have this this linear curve in orange. We have this looks like probably cubic curve in blue, and then maybe quartic curve in black, and then this super high dimensional polynomial curve in green to fit this data. If you were to pick one of these curves to fit this data, you think is like probably the true relationship in the data, which one would you pick? Just shout out a number, or not a number, a color. Here in blue, black maybe. Yeah, I probably pick blue as well. Black has this kind of uptick at the end, which I don't like. I'm not really seeing that, so I think I'd probably go with something like blue. Yeah, and you can see that obviously green is very overfit, and so if you try to apply green to predict new points, it's probably going to have a hard time. Orange is extremely underfit, to where you're going to have error due to basically not being flexible enough to handle this kind of concave curve at the top of our data. And so the second diagram on the x-axis is basically scanning over the flexibility of these models, with on the far left being our orange curve, and on the far right being our green curve, our high dimensional green curve. And so this red curve shows the error on our test data, and this gray curve shows the error on our training data. And so you can see that as we increase the dimensionality of the fitted curve, we can make our training error go almost to zero. But as a consequence, our test error increases. On the other hand, we can have if we are underfit, we will have both poor train performance, but also probably poor test performance. So the sweet spot is going to be somewhere here in the middle, where we are close enough to fit the true trend in our training data, but not not overfit to the point where we start performing poorly on our test data. Any questions on those graphs? All right, so some things that we're going to see come back over and over when we're talking about regularization. Generally, regularization tries to reduce overfitting by favoring simpler models. There's going to be this idea of a bias variance trade-off, where we can increase the variance of our predictions. Basically as we are regularization, so if we look at this graph here, regularization will push our model complexity towards zero, which reduces the variance of our model predictions, but increases the bias of them. And then our prediction error is the sum of the bias and the variance. And so the sweet spot will be at a place where we are hopefully minimizing both the error due to the bias of our predictions and error due to the variance of our predictions. Yeah, question. I'm not referring to the bias terms that we add to each layer of our neural network. I'm talking about basically the bias of our network predictions. So whether they are shifted up or shifted down. And yeah, so we're not going to cover this bias variance trade-off is it's pretty nuanced. And so if you want, we're not going to go very much in detail into it today, but if you're interested in learning more, Google the bias variance decomposition of the mean squared error. And there's a proof on Wikipedia that I think helps to make a lot more sense. Again, that's the bias variance decomposition of mean squared error. And it shows you basically how the mean squared error of your network can be decomposed into a term representing the variance of your model predictions and the bias of your model predictions. We're not going to be talking about Bayesian math estimation, but yeah, we are going to talk a lot about sparsity, which is basically how certain regularizers basically push our network weights to 0. Yeah, so a little bit more on the bias variance trade-off. So that is an example of matrix designer overfitting. So I'm sure that fits one person very, very well. Yeah, so when you in the back asked a question about when we're talking about bias and variance, what are we talking about? We're talking about our model predictions. And so a model with low bias and high variance will produce predictions that are clustered very close to the true values and tightly clustered. A model with high bias and low variance will produce predictions that are tightly clustered but shifted. High variance will make predictions that are generally scattered but have the correct, but are centered at the correct point. And then high bias, high variance will produce predictions that are both shifted and scattered.
So these just like the opposite characters.
Yeah, so low bias would be more accurate, and then low variance would be higher precision. Yeah. And so, yeah, in general, and this is why this is so applicable to neural networks. As a method tries to match more data points more closely, or as you increase the parameters of your model or use a more flexible method, we're able to reduce the bias or our training loss, but increase our variance, resulting in increasing our test loss. So this is these are basically the most common types of regularization that you will see. So our regularization will be a term in our loss function. And so here we have our total loss is a sum of our, what is the name of this loss function? Do you recognize it? Cross entropy, or maybe we call it negative log likelihood or maximum likelihood. Yeah, exactly. And then that's our normal cross entropy loss. And then we have a lambda weighting term. So this is what's called a hyperparameter, which we will choose. Basically, we will choose lambda to control our trade-off between regularization and minimizing our loss. As far as what that regularization can be, here are 3 common choices. This first one is called L2 regularization, and it basically penalizes the squared values of our network weights. The second one is called L1 regularization, and it penalizes the absolute value of our network weights. then this last one is a weighted sum of those two other of L1 and L2, and that's called elastic net regularization. Can you think of why penalizing the square of our weights or the absolute value of our weights could prevent overfitting? Yeah, Andrew? I'm sorry. What's Spencer? Spencer. Okay.
Basically, ones that have more error are less.
So you said
So ones with higher loss
weights with higher
impacts or like don't keep the weight as dramatic, like don't have the effect. It's subtractive based on.
So you're saying that if we have a large loss, if we have a data point leading to a large loss, it will not change the weight as much?
No,
Okay.
sorry, other way around. The ones that are correct change your flags. Like get updated less than. If they're closer, you don't need to fix it.
I'm not 100% sure I understand what you're saying.
Maybe
Yeah. What were you to say?
So during last week's reading, I struggled with this a little bit, and the way that helped me understand it is if I just look at the loss function as being what's in the red box up there, you're essentially fighting a higher order polynomial curve fit if you think of your network as a big curve fit. So in the previous few slides, we saw the very overfit example with lots of subtle curves in it. So you can think of that as a lot of very specific weights being used versus a simpler model that has just fewer components.
Yeah, so I think you're getting at the right idea. So yeah, basically he's drawing the analogy between high dimensional polynomials and high parameter neural networks, and a way to prevent overfitting with polynomial curve fitting is to reduce the dimension of the polynomial. And the analogy for that in neural networks is controlling the magnitude of our weights. Basically, you can imagine it as we don't allow our network to learn connections that are too strong, because we're going to just kind of assume that simpler is better. Yeah, what do you think? Good question. The question is, are higher order P norms ever used here? The answer is people do use them, but I haven't seen them used very commonly outside of just these two basic types of regularization or some combination of them. Though we are going to talk about in a couple of slides how different types of norms kind of affect the sparsity characteristics of what kind of model we run. Yeah, question. That is a very insightful question. How does reducing the magnitude of the weights make the model any simpler? And I think the best answer that I can tell you is kind of a hand-wavy explanation like the one I just gave you. Empirically, it seems to work. Like using these helps us generalize the test sets better. But yeah, if you think about it, like, is a network with smaller weights really any more simple than a network with large weights? It's a good question, and I don't think I have a good answer for you other than the fact that, yeah, what do you think? Yeah, that's an interesting intuition. Yeah, so That's the thought that, yeah, a high weight would seem to be concentrating a lot of information in one neuron, whereas regularization forces you to spread out the knowledge that's learned across many neurons. Yeah. Yeah, no, that's a fair point.
The problem is if that weight is wrong, then part of it takes it's like, I mean, it still takes work, but it doesn't take nearly as much practice. Like,
yeah, what do you think?
Out of 5, that would be
In the trait set. Yeah. Yeah, I think that's a reasonable explanation. But think about it. Yeah, and for your final project, you might yeah, explore something about regularization. Okay, so here we're going to talk about basically the effects of this regularizer. So if we were to imagine our unregularized loss surface with respect to parameter 1 and parameter 2, you can imagine it looking like this bullseye curve where the middle is the lowest point and the loss gets higher as you move away from those optimal weight values. So that's the first term of our loss, our cross entity loss. Then our regularization loss, you can think of being a different surface, and it will be 0. The loss will be 0 when the weights are 0, because remember we're penalizing the largeness of the weights. And so this blue bowl is also a curved surface. And then our summed loss is the sum of these two curves, which you can imagine being kind of the intersection of two bowls. And the optimal weights will, in the case of L2 regularization, will occur at the intersection of those two bowls. And so this is a line that is correct for L2 regularization. The combined minimum will lie on the line between the minimum of the square error and the origin, assuming our square error is also hyperbolic change. So there are a couple of different norms that we can use. This is the L2 Euclidean norm, analyzing the square of the weights. And the loss surface for that looks like a bowl. This is, I wish we had a picture that was in 3D, because this is just taking a cross section through that loss surface. Where this circle is just saying this is when this sum of squares is equal to 1. Then this is our L1 norm, and this diamond shaped curve is when our L1 norm is equal to 1. And you can see that as it reaches 1 when W1 equals 1 and W2 equals 0, and also reaches 1 when W2 equals 1 and W1 equals 0. And then yeah, and then as you shrink one and increase the other linearly, you end up with a straight line between those 2 points. The Minkowski norm is a more general case, where it can be taking the p, taking a to the p and then taking the p root of it. And so this is p equals 0.5. You get this concave curve. And then with p equals infinity, you end up with this max norm. And then finally, the L0 norm is the number of the limit as we take p to 0. We get basically just this cross where it's the count of non-zero elements. And so we're just going to focus though on L2 and L1. So they have some interesting properties. So also L2 regularization is called ridge regression, and L1 regularization is called lasso regression. And we were talking about how the loss, the total loss is the sum of these two of our normal loss function plus our regularization. And for ridge regression, it's that loss is going to be optimized about at the intersection of those two goals. It's the same case for lasso regression, but in this case, our goal is actually going to be more like, what is that shape called? It's like a pyramid, and it's going to be like an inverted pyramid. And so that the loss at 0 will be 0, and then as you basically go up the sides of the pyramid, your loss increases. And as a result, lasso regression is more likely to intersect with this true loss goal at a place where one of our weights is equal to 0. And this is an effect that can cause sparsity in your neural network. And what that looks like is certain weights of your neural network in lasso regression are more likely to get set equal to 0. Whereas that is not the case with ridge regression. Ridge regression is more likely to just shrink the value of your weights. Any questions on this picture? Yeah. That is a good question. The question is whether sparsity helps with computational efficiency in gradient descent and or in taking forward passes. And the answer is kind of, but actually we don't have a lot of really good sparse algorithms. So in theory, probably, but on current hardware, we find that yeah, it's really hard to see significant benefits due to sparsity.